Hello everyone and welcome back to Computer Science for Everyone. In this video we're going to be creating our tree and we're going to be finding out how to add and find nodes in our tree. In the previous video we were creating our node and we found out that we had a name, phone and ID as well as a left and right child. We changed our methods and changed our constructor in order to reflect those changes. However, we forgot an important method that is going to come into play later on. And this is a method that will give us the number of children this node has. So a method that will tell us whether we have 2, 1, or no children. We can create this method here at the bottom, and it's going to be a fairly simple method. That is, however, going to show us a couple things about how Boolean comparisons work. So I'm going to create a public int method because it's going to return 0, 1, or 2, depending on the number of children we have. And I'm going to call it getChildren. So now, if neither of the two nodes is null, it means that both of them exist, and therefore we have 2 children. So if left is not equal to null, and right is not equal to null, both of them are not equal to null, and so we return 2. Else, if left is not equal to null, or right is not equal to null. So you might be wondering, how does this work? And it is a very good question. If neither of the two are null, we are going to return 2, and we are never going to check for this. However, if one of them is null, then this will not run. This will be false. If one of them is null, this will be false, because not both of them will be true. So if one of them is null, then not null and not null is not true. So we jump onto this else if. And in this else if, we test if one of the two of them is not null. So if left is not null, or right is not null, we return 1, because we know that although if both were not null, this would return true. If both were not null, we would have returned 2 in here. So if both are not null, we return 2. If one of the two is not null, we return 1. And if not, we return 0. So that's that method. And this is everything we needed to do in the node. Now let's go back to the tree and start creating the tree itself. So the tree is going to have a root, that is the beginning of the tree. And then it's going to have the setters and getters for the root. So get root is going to be of type node. Like so. So we have the getter and setter. Now I also want a method that will tell us whether the tree is empty or not. So the tree is empty if the root is null. If the root is not null, then the tree is not empty. Sorry about that. So how would we test if the tree is empty? If root equals null. So root equals null will return true and the tree is empty, or it will return false if the tree is not empty. Because it returns true or false, we can directly return that from our method as well. So in here we're returning whether root equals null or not. So in our Boolean method, this will return true if the root is null, or false if it is not null, i.e. true if the tree is empty, or false if it is not empty. Next up, we want to be able to add a node. And we have seen how this works in theory, but we haven't gotten around to implementing it. So let's take a look at how we could do this. We're going to use something called recursion that is fairly simple to understand. I'm sure you won't have a problem with it, with the way that it is explained in here. So what I'm going to do is I'm going to do public Boolean add And then it's going to take a new node. And it's also going to take a parent node, or where what the parent of the node that we're trying to add is. And then it starts to get a bit more complicated. If okay, so what am I testing here? If new1.getID, this is going to give me the ID of the new one, equals the parent's ID. How is this possible? Well, if we're trying to add a node, and we come across that the node we're trying to add already exists because another node has the same key, then we want to return false and not add a node. We don't do anything with this. Else, if the new one's ID is less than the parent's ID, we're going to do something. And finally, if the new one's ID is greater than the parent's ID, we're going to do something else. So here we test if they're equal. Here we test if they're smaller. So in the else, the only other option that is left is that it is greater. So let me just add a couple spaces here for your readability. And if I'm looking towards the camera at some point, it's because I do have the notes of what I'm saying here. So that is why, so I don't make any mistakes. That would be really bad. So yeah, the new node belongs to the left of the parent, and in here, the new node belongs to the right of the parent. So if it is at the left, what do we want to do? We want, first of all, to check if the parent's ID, sorry, if the parent's we want to check if the parent's left is null. Why do we want to check this? If we're about to add a new node that is going to go at the left of the parent, we have two options. Either we put it directly at the left, or we have to move down the left part of the tree in order to add it later on at the end of the tree. So if the parent's left node is null, it means that we have to add the new node directly below the parent because it doesn't have a left node. Like so. So if the parent's left node is null, it doesn't have a node to its left, the new one belongs to the left, and therefore we put it at the left. If the parent's left node is not null, then we have to move down. So here is where recursion comes into place. How do we move down this tree? Well, this add method is trying to add a new node below the parent. So what if we call this method again from within itself with a new node, but instead of the current parent, we move the parent down to the left. So what this does is that whereas the parent could be, for example, the root, here we call the same method again, but instead of the root, we moved to the left in the tree. Next time, we would move to the left again, and so on until we get to an empty node, where we would do this, because the parent's left would be null. So this is everything there is to recursion, really. It's just calling a method from within itself. That is called recursion. After setting the parent's left, we want to return true, because it means we have essentially added a node, and this is the objective of this method. So if this method returns true, it's because we've changed the node. If it returns false, it's because we failed to change node. And the same thing applies when the node belongs to the right of the parent. Only here, if the parent's get right is null, then parent set right We set the parents is right to be the new node, and we return true. If not, we simply call the same method again, but the parent moved to the right instead of staying in the same place. So what this is going to do is going to call itself again, but instead of the parent, it's going to be the parent's right node. So it's essentially going to move down the right path of the tree. Finally, if nothing succeeds, we return false in here. If we haven't been able to add a node in either of these cases, and the new one is not equal to the parent, we return false here. To be honest, we're never really going to get down here, because any of these three is going to happen eventually. But just to keep this happy, we'll have to put return false in here. Okay, so that is how we add a node below a parent. What if we wanted to add a new node just anywhere in the tree? What I mean with this is, if we wanted to add a node starting at the root, let me explain what I mean with a very easy example. Add this method we just created. We give it the new node we're trying to add and a potential parent for this node. So let's say that we had this piece of software. Let's say that we had a node with the value 5, a node with the value 7, a node with the value 3, like so. And we wanted to add a node with a value 2. So we would obviously add it down here. But what if we don't know any of these nodes except 5? In our method, we would give this as a parent node. We would give the 5 as a parent node. And then we would have our 2 here. So new one would be 2. The parent would be 5. The ID of new one is less than the parent's ID. I agree with that. If parent get left is null, we set the parent's is left to be the new one. Is the parent's is left null? No, it is not. It is 3. So what do we do instead? We add again new one and parents get left. So now this comes down here. This is now the parent in the new call of the method. If the IDs are the same, return false. The IDs are not the same. New one's get ID is less than parent's ID. Yes, it is. 2 is less than 3. And the parent's is left is null. Yes, it is. There's nothing down here. So what we do is we set to the left of the parent to be the new one. Like so. And then we return true and we exit the method. So this is how that goes. And when we return true, then down here, we also return true. So we end up returning true in both times. And that is recursion, and this is how that tree would end up looking like. Simply putting the 3 below to the left of the, putting the 2 to the left of the 3. Okay, so what else is there to do? We have to be able to find nodes. So let's say we have a method called find, and we give it the ID to find. Well, we could use recursion here again, but because loops are faster, I am going to use a loop instead. So I'm going to create the marker node, that as we've seen many times, it used to keep track of where we are in our tree. And then I'm going to do, while the marker is not null, what do we want to do? I'm going to want to move left or right depending on whether the ID to find is less than or greater than the ID of the marker. So instead of that, if the ID to find is greater than the ID of the marker, then marker equals marker.getRight. Let's see how I've arrived to this. Let's see we are at 5 and we're trying to look for 7. 7 is greater than 5, so now we move the marker to be the marker's right, i.e. 7. So the marker is now 7. And now we have to check for whether they're equal or not. The other option, however, before that, is if ID to find is less than marker get ID, in which case marker is marker get left. The last option is if they're equal, in which case we return marker, because they're both equal. So if we return marker, marker is going to be the one that has the same ID as the ID we're looking for. Down here, if we fail to return marker at any point, it's because we haven't been able to find the node. So we return null. And that is our find method. Now, we haven't seen how to delete nodes yet, but we have seen in the presentation that in order to delete a node that has 2 children, we're going to have to find the rightmost node in the left subtree or the leftmost node in the right subtree. So I'm going to create a method that will give me the rightmost node in the left subtree of a node. So it's going to be called find rightmost, and it's going to take a node in which it's going to begin the search, and then it's going to spit out the node that it finds, i.e. the rightmost node. How is this going to work? Well, it's going to be really similar, actually, to the find method. We're going to have a marker node, but instead of the root, it's going to start at the start here, the node we give it. Remember that it is the rightmost node of the left subtree. So instead of a start, I'm going to start at the start's left. And then, once again, while the marker is not null, then we're going to do something because we haven't gotten to the end of the place yet. If the marker is not null, then I want to move to the right because I'm looking for the rightmost node. So going back to this program, let's say we have another node here that has the value 4. If I'm starting at node 5, then marker is start.getLeft, which is 3. I want to move marker down to the right, because that will give me the rightmost node. If I ever move it to the left, it's not going to give me the rightmost node, because the left child of any node is always going to be less than the value of the node itself. So the rightmost node is going to give me the largest value of a node that isn't larger than the root. So 4 is the largest possible value that is smaller than the root value. And we have seen why we want this in the how to delete a node lecture. So now that we have this, we can continue going down our tree. While the marker is not null, then we create the right node of the marker. If the right is not null, it means that there is still a writer node, writer if that is a word, there is still a node that is more to the right, and therefore we want to get that node instead of the marker. So if the right is not null, marker equals marker.getRight. If it is null, then we return marker. And if we haven't been able to find anything, we simply return null. So that is that, how we find the rightmost node in a subtree. So we're going to give it the node we're starting from, and then we're going to find the rightmost node in that node's left subtree. One last thing that is going to come in handy is the find parent, in order to be able to find the parent of a node. This is going to be really useful when deleting nodes, and you'll see why in a moment in the next video. So we're going to give it an ID, and we're going to find the parent of the node that has that ID. So if we gave it the value 3, it will give us the node 5, because 5 is the parent of 3. So how do we do this? Well, it's going to be really similar to find, so I'm just going to copy find, put it down here, so we create our marker, which is equal to the root. While the marker is not null, then we're going to do something a bit different. And I don't want to make any mistake here, so I'm just going to look at my notes. Okay. So the first thing we want to do is create the left and right nodes of our marker node. This is so we can check for whether either the left or the right node has the ID we're looking for. If either the left or right nodes have that ID, then we want to return the marker. If we didn't create these two, and we just went with the ID, then we wouldn't be able to return the parent. We would only be able to return the actual node that has the ID. So, if the marker's ID equals the ID to find, this means that essentially we are at the root, because the root doesn't have a parent. And so if the marker's ID is the ID to find, means that we must be at the root. And you'll see why in a second. So we return marker. In what other cases do we want to return the marker? If the left node has the same ID. Or if the right node has the same ID. So if the marker left ID or right ID have the ID to find, we return the marker. Here you see why we will only return the root if it has the ID to find. Let's see what I mean with this. Let's say we're looking for the number 3. So we start here the root with our marker, and we have left, which is 3, and right is 7. So what we do is we check. Is the marker's ID equal to 3? No, it's not, because it's 5. Is the left's ID equal to 3? Yes, it is. So we return marker 5, which is the parent. However, what if we were looking for 5, which is the root? There is no parent. So if we didn't have this section of code here, nothing would ever check that 5 has the ID, because 5 is not a parent of anything. 5 is not a child of anything. So that is why we check for it. The marker's ID is also the ID to find. And if it is, we'll return the marker, because that is the only node that doesn't have any parents. There is one last problem. What if left or right are null because the node doesn't have a child? This is why we check that left is not null and right is not null. So what happens here is that if left is null, because this is an AND, we just don't check this. This is a brilliant feature about Java. If left is null, it knows that this is false. False and something is always false, because AND needs both to be true. So if the first side is false, it doesn't check the right side. If it did check the right side, we would get an error, because if left is null, we can't call getID on something that's null. But because Java does this, we do not check the right side, because it knows that false and anything is false, so it doesn't need to check. So if left is not null, then it checks that the left's ID is the ID to find. If both of them are true, because these are OR, this is true, anything or true or anything is true, so we return marker. Notice how the brackets here are extremely useful in this instance. Similarly, I do the same for the right. So if this or this is true, right is not null, and the right side is the ID to find, we return marker. And finally, the last OR joins those two, joins either of those two with the marker's ID is the ID to find. The other option is that the ID to find is less than the marker's ID, in which case we make the marker equal to marker.getLeft. And finally, that the ID is greater, so we simply move left or right, depending on whether it's less than or greater than. Finally, we return null, of course, if we cannot find anything. So this is how to find and add nodes in a binary tree. I know this was a long lecture, a long programming video, and trust me, it's going to be vital that you understand how the binary tree is working. This program here is not free, but it is great. But when I was programming, I did it in paper with a pen. So I highly suggest you draw the trees, see how these methods are working, try to test them about. Because in the next video, we're going to do deleting nodes, and that is a lot more complicated. So stay tuned, let's go into the next one, and then we'll be pretty much done with binary trees. So I'll see you there.